Transition metals form large number of complex compounds in which the metal atom are bound to a number of anions or neutral molecules. Such compounds called coordination compounds. So this is a definition of transition metals coordination compounds. This is a periodic table, and remember, transition metals predominantly show coordination compounds formation, although we also do have coordination compounds with magnesium and other alkali or p-block element metals, but they are predominantly shown by transition elements only. Like we having a manganese complexes, iron hemoglobin, cobalt complex, which is a vitamin B12, and many more to count, which are transition metal complexes. Now, how the coordination chemistry started? The beginning of a coordination chemistry was with the simple experiment of cobalt ammonia chloride complexes that you see here in aqueous solutions, and these were performed by a scientist known as Alfred Werner. He was a Swedish scientist. In his experiment with cobalt 3 chloride with ammonia, he found certain observations, like in this cobalt chloride ammonia complexes, or we should say compounds at that point of time, if you add a silver nitrate in excess, we have certain precipitates coming out. Again, we are getting a precipitation, and that precipitation varies from one compound to other based on the color. Let's see, like what he saw, that a compound which was yellow in color, formula is same. That precipitates that every 1 mole of that compound precipitate uses 3 moles of silver chloride. 3 moles of silver is used. Next compound, which is purple in color, its chemical formula is same, but it precipitates only 2 moles of silver chloride compared to 3 moles of silver chloride. It means only 2 moles of chloride are present in that compound for ionization or precipitation. Next compound, which is green in color, what he got? Only 1 mole of silver chloride is precipitated, which means only 1 chloride group is present for precipitation. Finally, again, another compound, which is violet in color. It's 2 having the same 1-to-1 electrolytic precipitation. Six groups in all, either chloride ions or ammonia molecules or both, remain bounded to the cobalt ion during the reaction. As we discussed in definitions, coordination sphere, this is a coordination sphere, it will not ionize. Only counter ion or ionizable part will be available in solution, and that's why it will react with added silver nitrate and precipitated as silver chloride. So from that, he could draw certain conclusions, like although the molecular formula or weight is remain the same, because all these compounds having the same molecular weight, but their ionizable parts vary. He also do certain conduction experiments on these, and on based of his experiments, what he said, he called a single entity which does not dissociate under the reaction conditions is a secondary valency. He called whatever we are calling as a coordination sphere as secondary valency, which does not ionize, an ionizable part as counterions or primary valency. So this was the beginning of coordination chemistry. In coordination compounds, metals show two types of linkages, primary valency, secondary valency. Just we saw secondary valency is the one, this is a coordination sphere in square brackets that do not ionize. Primary valency, it do ionize or goes into solution, available for reaction. This is non-ionizable, this is ionizable. Secondary valency is equal to coordination number and is fixed for a metal having a characteristic spatial arrangement corresponding to the coordination number. So these secondary valency ligands provide a coordination number for the complex. There is another form of coordination compounds, or the resembles to coordination compounds known as double salts. What are double salts? Double salts are obtained by combination of two different salts which were crystallized in the same regular ionic lattice, but these salts dissociates completely in aqueous solutions. Let's see double salts. Both double salts and coordinate compounds formed by the combination of two or more stable compounds in stoichiometric ratios. So this is a similarity in that they formed in the same way, but they differ in the solubility, as double salts like common name is kernolite, which is potassium chloride, magnesium dichloride with hydrated water, which is completely dissolved in water to give us the potassium, magnesium and chloride ions. More salt, which is iron sulfate, ammonium sulfate, and when you dissolve again, you're getting a complete ferrous ions, ammonium ions and sulfate. Potassium alum, common name, potassium aluminium sulfate, again when we dissolve that in water, it completely dissociates to give us potassium, aluminium and sulfate. So the primary difference between coordination compounds and double salts is on solubilizing in aqueous solution, double salts completely dissociates to furnish basic ions, and coordination compounds do not so. We dissolve the double salts, like we have dissolved here our more salt, we are getting the iron, sulfate and ammonium ions. Now we will discuss about rules applied while writing the formulas of mononuclear coordination entity. Mononuclear means the coordination compounds that will have single metal atom. So first of all, we list central atom, like we have chromium here. the ligands and the polydentate ligands are listed in alphabetical order. We follow in an alphabetical manner, like here. The formula for the entire coordination entity, whether charged or not, is enclosed in a square bracket without any space. The charge is indicated outside the square bracket as a right superscript. It is a charge on the coordination sphere, and it may be positive or it may be negative. How to name it? Like if we have to name this complex, first name of the ligands present within the square brackets. These are the square brackets of coordination sphere. We name them alphabetical order and add di, tri, tetra before the ligand. First we consider the name of these ligands, then we add it depending upon the number of ligands present as a di, tri or tetra. Like here for ammonia it's amine, for water it's aqua, and in alphabetical both are A, but we know M comes before Q, so you start with amine. So as the anionic ligands, the names also bromide, bromo, fluoride, fluoro, oxo for oxygen, hydroxo for OH group, cyanide, cyano, oxalic acid, oxalato, carbonate, carbonato, acetic acid, acetate. For neutral molecules like ammonia and water, amine, remember M is double, water aqua, NO nitrous oil, carbon oil, oxygen molecule, dioxygen, nitrogen, dinitrogen. This is pyridine, this is ethylene. Many other such possibilities. In next step, if the complex ion is cation, the metal is named same as the element. In case of a cationic species like here is a cation, the central metal atom is named same as its original name, like chromium. If chromium is in a complex of cationic complex, we call it chromium only. Pt, platinum is platinum only. If the complex ion is an anion, name of the metal end fixed with a suffix "ate", like chromium will be chromate, iron will be ferrite, and cobalt will be cobaltate. So "ate" will be fixed as a suffix to the name of central metal atom. This is a neutral platinum complex, no charge on the coordination sphere. In neutral complexes also, there is no charge. We just simply name central metal atom with the prefix N having a 2 dashes separate. This is in case of neutral complexes. So cationic and neutral complexes having the same metal name. Anionic complexes will have chromate, ferrite or cobaltate. Third step is oxidation state of the metal in cation, anion or neutral coordination entity is indicated by Roman numerals in parentheses. So coordination or oxidation state of the metal atom is indicated by the number, Roman number in parentheses, which is suffixed to metal name. Like in this complex, we are having a hydroxyl, which is a 4 tetrahydroxyl. We are having the zinc, and because here is the potassium, which are cations, so counter charge will be anionic. That's why it will be zincate. Let's calculate the oxidation state of the zinc here. It will be zinc hydroxy -4 and here -2. So calculation will be 2 positive. We get zinc, we get a 2 positive charge, which is indicated after the zincate in parenthesis. Next step, counterion is named as, in case of counterion is anion, it is named after the Roman numerals. Here we are having a chloride, it's a cationic species, and this name means this counterion or primary valence name after the Roman numerals of central metal atom. Like here we are having a 1 amine cobalt carbonate, then its name will be pentaamine carbonato cobalt, which is here is a 3 oxidation number of cobalt because carbonate having a -2, and its cationic vacancy will be +1 equal +1, and +3 will be total charge on cobalt, so which is 3, and chloride counterion after the Roman numerals of complex. In case counterion is cation, it is named before the naming of ions. Here zinc got a 2+ oxidation state after calculations and it's a cationic species, so name it first potassium tetrahydroxo zincate, because it's anionic, and 2 Roman numerals which indicate the charge on central metal atom. The same way, some complexes names have been given. Like this is a cationic complex, so zinc metal will be cobalt, same. Charge on the cobalt will be carbonate having a -2 and +1. So cobalt plus ammonia 0, carbonate -2 is equal to +1. Cobalt charge will be +1. Negative turns up positive because it shifts on the other side of it. Equality +3, which is +3 charge here. So name will be pentaamine carbonato. It's a cationic species, cobalt 3 chloride. Because anionic, when counterion is an anion, it is named after the metal atoms, Roman numerals. Next, it's again anionic, so cationic coordination sphere. It will be tetra aqua dichloro chromium -2 +3 chloride. Here it is anionic coordination sphere, so potassium is a nitrido, first pentachloro nitrido, then osmium, so name will be osmiate 6, because what we'll get osmium and 2 negative should be 7 actually. So nitrogen also having a certain charge, so it will be 6. Here we are having again potassium, so it is a ionic complex named as ferrite. Potassium, first pentacyano nitrosoil, which is neutral, then ferrite 2 positive. Why? 3 negative, and Here is negative 5. First, iron plus minus 5 cyanide plus 0 nitrous oil is equal to minus 3 counter charge. Now minus 5 turns up to the other side of equality. It will be plus 5 minus 3 will be 2. Now, few more coordination compounds, like you see here. This is a hexamine cobalt trichloride. Again, this is a, here counter ions are not present, so we will simply name hexamine cobalt 3. Here dichloride is present, pentamine chloro cobalt 3 trichloride. And you see here only difference is coordination sphere. In one chloro is present inside, other is present outside. And similarly here, pentamine, we are having a chloro cobalt 3 positive. Then we have a tetramine chloro, then nitrito. This no O mean is directly bound to nitrogen, and then 3 chloride. Tetramine chloro nitrito cobalt 3 is a charge. Diamine, then we are having in this compound besamine. Then we are having a chloro group, chloro, ethylene, ethylamine, platinum, chloride, which is a methyl group here, methylamine. Next complexes, we are having ammonia, methylamine, chloro, and it's unipositive. Counter ion is missing. Same name, only chloride will be missing. Diamine, it's a besamine. Both possibilities are there. In this compound, we are having a coordination sphere. Copper is a central metal atom. We are having a 2 chlorine. Then we are having a urea. This NH2CO means nothing but urea. 2 molecules, it's a neutral molecule. And so it will be dichloro bis urea, copper 2. Then again platinum complex, anionic species, so it will be named as pladate. Tetrachloro was potassium before it because it's an anionic complex, and cation is our primary valency. Potassium tetrachloro pladate, charge will be 2 positive. 2 negative is a counter charge, which is equal to sign platinum plus negative 4 equal to minus 2. Negative 4 will go to the other side of equality, plus 4 minus 2, 2 positive. So metal atom acquires 2 positive charge.